In chapters 5 and 7, we discussed electrostatics and magnetostatics, which discussed time-invariant signals. Now, we learn about time-varying signals, which builds on what we've learned and just adds a little bit more of a variation and includes some extra terms in the Maxwell's equations that include time derivatives and also how electric and magnetic fields couple, creating electromagnetic waves. Anyone that understands the basic concept of the majority of our electrical generation knows that a varying magnetic field in an electrically conducting material, copper wire, creates electricity. This is the chapter in which we learn why that is. Not only do we find out why a current is induced, but we also learn why the induced current opposes the change in the magnetic field. This intuitively makes sense because we know that a generator with a load will require more energy to be turned than one without a load. We also go into why we say current is induced when, in reality, a voltage is induced from which the current flows. It is interesting to note that this electromagnetic induction can also be done with a transformer if the field is changing. This is the case of extrapolating from a single loop of motionless wire that is within a time-varying magnetic field and figuring out what happens when you increase the loops. To give this electromagnetic induction a more thorough picture, we learn about Faraday's law, which describes the generation of electric potential, or voltage, with a time-varying magnetic flux. Though we start learning about electromagnetic induction conceptually, Faraday's law gives it a rigorous mathematical treatment. We then take this math and expand on it to give mathematical representations for all of the concepts we learn, such as transformers and power generation. We wrap up this chapter with a mathematical derivative representation showing how the change of an electric field and its position change in a magnet with time. This form shows how electric and magnetic fields are coupled at each point in space, which has important ramifications in understanding how these fields work.